Hello, ladies and gentlemen. Today we're going to be talking about forces. Specifically, this is about section 4.1 and forces in one direction. I'm sorry, one dimension. So what a force is a physical push or pull on an object, and it's a vector quantity. And remember that a vector has both a magnitude and a direction. So a force, meaning how big is the force? And in the direction is exactly what it states. In what direction? Are you pushing down on something? Are you pulling up on something? Are you pulling it forward? Are you pulling it at an angle? Now, your book says that there is two different types of force, and this is not true. Your book says that there's a contact force. When something is directly pushed or pulled, like this young man here, he is physically pushing and touching something. And then it says that the other type of force is a field force. That's when the object is not touched, like gravity or magnetism. So you can pull on something from across the void without physically touching them. But that's really not true. This is what science currently says about forces. Science says that there are four forces right now. The first one is electromagnetism. So a magnet, gravity, the strong nuclear force. This is what keeps protons and neutrons attached inside of a nucleus. And then the weak nuclear force. These are the four fundamental forces. The weak nuclear force is responsible for nuclear decay. We're not really going to talk about the strong or weak this year at all. And you might be saying to yourself, hey, Mr. Hare, how can this be? In this one before, a force is a push or a pull. How is if I physically push something, which one of these four is it? Well, believe it or not, it's actually electromagnetism. The atoms in your hand, when you physically touch something, the electron repulsion between the object you're touching and your hand, that electron repulsion is what's physically pushing it. It's a really weird thing. But when you touch something, you're not actually touching it. It's just your brain perceiving that you're touching something. You're not physically touching it. The electrons are repelling one another from the other thing, and that's electromagnetism. When we talk about forces, sometimes it's handy to make a picture, and we call these pictures free body diagrams. A free body diagram, all it is a drawing that labels the forces that are acting upon an object. For instance, in this right here, we've got a ball hanging on a string. So what you do, here's the ball, and you just label the forces that are on it. So gravity is pulling it down, and then you've got the rope pulling it up. You've got the ball over here, supported by someone's hand. Here's the ball. You've got gravity pulling it down again, and the hand supporting it. There's a couple of examples that your book has where it says to make these free body diagrams. So, like number one, it says a flower pot that's falling freely from a windowsill. Here's my flower pot, and gravity pulls it down. You're going to have gravity everywhere you deal with forces. And there's nothing opposing it unless there's air resistance. It depends if you're thinking about air resistance or not. Number two, skydiver, falling downward, hoping his parachute will open. At a constant velocity, this is big. Constant velocity means that you've got gravity pulling you down, but you've got air resistance at the exact same amount. And you're going to move at a constant velocity. We'll talk about that a little bit more. Number three, a cable's pulling a crate at a constant speed. So here's my crate. I'm pulling this with a force of pull. And then again, constant speed. That means that there's friction. Remember, there's also gravity pulling down on this thing. And then there's another force that you'll be introduced to a little bit later called the normal force. The normal force is a supporting force provided by the surface that you're resting on. It's always at a right angle to the surface. Now, when we do free body diagrams, you've noticed that all of my arrows always go from the object. I'd never put my air resistance pointing at the person. Like, all of my arrows go away from the object, and that's typically what we do inside of free body diagrams. Now, if we've got a couple of forces acting on something, we call the one force that you can simplify them all as the net force. So, for instance, I've got all these kids pulling on a box. So let's say I had a box or something, and I've got person number one pulling this way with maybe a force of like 10 pounds, and then person over here pulling this way with 8 pounds. The net force. This 8 cancels off this 10, and the net force is equal to 2 pounds. And notice I try to draw my arrows the right length. So bigger forces have really long arrows that shows the magnitude. Smaller forces have smaller ones. So the net force is the total combined sum, vector sum of the forces. Now, if something happens to cancel out, like going back to this example here, if I said it wasn't 8 pounds, maybe they're pulling the opposite way at 10 pounds, this would be an equilibrium, meaning that the forces cancel each other out and the net force is equal to 0. If you have a net force equal to 0, that doesn't mean that there's no forces on it. It just means that the forces that are acting on it cancel each other out. They're equal and opposite. So we've got this one here in letter B here. These kids are pulling in opposite directions on this table. So this is a net force of equal to 0. This is an equilibrium. Over here, both pulling in the same direction. One pushes, one pulls. The net force equals 200 newtons. And you'll learn what a newton is in a second. I've been using pounds up to this point, but newtons are something that you've never seen before. It's the metric unit of force. Then here I've got net force of, you want to maybe be careful? I would maybe say negative 100. If I said that positive was to the right, this would be negative 100. Or you can say that you have a net force of 100 newtons to the left. You remember that since force is a vector, you have to have a magnitude, how big, and a direction, positive or negative. Or you can use words to the left. Isaac Newton has been attributed to a lot of things dealing with force. He has 3 laws that bear his name. He is the founding father of physics, Isaac Newton. Everything that we're learning in this whole entire first semester is attributed to Isaac Newton. There was another guy that came along that upended everything that he did and said everything he did is wrong. And it is. The stuff that he teaches us, it works really well for stuff that's really fairly small and moving at fairly slow speeds. But when you start getting into the realm of atoms and galaxies and stars, it all breaks down. And that's where Albert Einstein made a name for himself. So Isaac Newton, his first law, it says an object in motion will remain in motion, and it even goes a little bit further than that, in a straight line. And an object that rests will remain at rest unless a force acts upon it. And let me show you a really cool example that I have. I looked up on YouTube. There was a Japanese astronaut who played baseball with himself on YouTube, and it's really, really neat. And you can see a prime example of objects in motion staying in motion in a perfect straight line. Like up in space, there's not a whole lot of gravity, but look how perfectly straight that ball moves. And look at him, too. As he moves across the space station, you'll see him moving in a perfect straight line. very crazy. Newton's second law. Newton's second law, well, sometimes this is known as the law of inertia. What inertia is an object's ability to resist change. Things that have inertia are massive things. More mass equals more inertia. More mass equals more inertia. Inertia is how hard it is to accelerate something, like to get it moving, to stop it moving, the law of inertia. The tendency of an object to resist change. His second law is F equals ma, meaning that the acceleration of an object is directly proportional to the net force acting on it, and indirectly. This is what this says. There's a lot of big words right here. This is saying that if you push on something, it will accelerate. The bigger the force, the bigger the acceleration. Or, if you keep your force constant, if you have a really big mass, then the acceleration isn't as big. Or if you've got a small mass, you'll have a large acceleration. Let me show you an example of that I found on YouTube. This guy, what he's got two cannons. The red ball is twice as heavy as the yellow ball. He's put them both into a cannon. He's going to fire both of these.
You're good? Good.
Under the same pressure,
so
and you're going to see which one
we're
accelerates
gonna
more
so
because one's lighter, one's heavier.
More than enough. And we're going to do a quick countdown and fire these at our brave volunteer.
Again, the red one, much heavier than the yellow one.
3, 2,
shot with the same
1,
force.
And
you can see
which one was going
that the red one went not anywhere near as far as the yellow one. In Newton's last law, it says for every action, there is an equal and opposite reaction. Kids can spout this off, but this is these are really difficult laws to truly have a conceptual grasp on. And so let me show you another example that I found of this. This was at MIT. This professor has not a rocket, but a carbon dioxide fire extinguisher hooked on the back of his tricycle. So what's going to happen is there's going to be an action. And you're going to have a reaction. The force pushing out the back pushes and propels this person forward. Now it's funny because the forces are equal and opposite. The force that is propelled this way is exactly equal to the force this way. The forces are the same. But because this guy has a large mass, then you get Newton's second law. The bigger the mass, the harder it is to accelerate. But the forces, when you push on something, it always pushes back against you with an equal and opposite reaction. We'll be doing a lot of stuff in class to kind of demonstrate all of that. I mentioned before that we're going to talk about the Newton. What the Newton is, it's a unit of mass times acceleration, because we had said before that F equals ma. Because mass is always in kilograms, and acceleration you learn is in meters per second squared. When you multiply these two things together, you get a kilogram meter per second squared. And physicists just don't like to keep writing that, so we just call it a Newton. So 1 Newton is equal to 1 kilogram meter per second squared. And what a Newton is, if you've got 1 Newton of force, what that will do, if you have 1 kilogram of an object, like I've got a kilogram mass on my desk, it will accelerate at 1 meter per second squared if I push on it with 1 Newton. That's exactly how this is defined. Mass and weight, they are both two different, one of them is a force, one of them is not. Mass is scalar, weight is a force. Weight is force. So weight is measured in newtons in the SI base unit. Sometimes we refer to pound force in the English world, but we're going to be dealing primarily with newtons. Your mass on the Earth is the same as your mass on the moon. Mass is just basically how many atoms you have. You put something that's very massive up in space and it doesn't weigh anything, but it's still hard to get it to start it and stop it moving. It still has mass. So we call that its inertial mass sometimes. We're going to see a bunch of forces throughout this semester. The first one is friction. Friction always opposes motion. So if you're moving to the right, friction will always be to the left. If you're moving down a hill, friction acts up the hill. The normal force. The normal force is, I mentioned it before, it's a supporting force that lifts an object. Springs. Springs can pull on something, and springs can push or pull if you squeeze them together or you stretch them out. That's why they call it a restoring force. Tension is provided by ropes, and they're always in the direction of the rope. You can't lasso something and then lift it. You can only lasso it and then pull, so forces only act in the direction of the rope. Thrust. Thrust is something, it's a propulsive force that moves something like rockets, planes, cars, and people. And then finally, weight. Weight always acts towards the center of mass. So like on Earth, it's going to be straight down towards the center of mass of Earth. Not the I'm sure the center of mass is very close to the actual center, but it's the center of mass. And that concludes everything we've got for this first section 4.1.